AB Calc 3.4, day number 2, sparse data. So let's assume that f of x and g of x are differentiable functions that we know very little about. In fact, assume that all we know about those functions, are in the table below. This isn't a lot of information. We wouldn't be able to tell, for example, what the derivative of f was at x equals 3 with any degree of accuracy. We could take a guess, but we don't know for sure. But we are still going to be able to figure out some things using the rules of differentiation. So let's say that h of x equals e to the x times f of x. It asks us to find h prime at 0. So first of all, let's find h prime at x, generally speaking. We're going to utilize the product rule here. So we're going to take the derivative of the first function, derivative of e to the x is e to the x, times the second function left alone, plus the first function left alone times the derivative of the second function, which we can leave generally in terms of f of x. So if I want to know h prime at 0, I'm going to insert a 0 everywhere that I see an x. And then I'm going to use the table in order to help me determine what the output would be in this situation. Okay, h prime at 0. Well, I know e to the 0 equals 1. So really all I want is f of 0 plus f prime at 0. Okay, so f of 0, we can see in the table, is 5. And f prime at 0 is 9. Therefore, h prime at 0, or the slope of the tangent line at x equals 0 for h of x, would equal 14. Okay, you can kind of see where we're going with this. So now I'm going to find, let's see here, j prime at 1. Okay, so to keep things simple here, I'm going to find the derivative of j of x, and I'm going to leave negative 4 kind of out of play right now. I'm going to use the product rule on the two inner functions. Okay, so that'd be f prime at x times g of x left alone, plus f of x times the derivative of g, or g prime of x. So j prime at positive 1 will equal negative 4 times f prime at 1 times g prime at 1 plus f at 1 times g prime at 1. Okay, so f prime at 1, what is that? That is negative 3. G at 1 is 2. F at 1 is 3. And g prime at 1 is 6. So j prime at 1 will equal negative 4 times the quantity, negative 3, times 2 plus 3 times 6. Okay, let's do a little simplifying here. And we get j prime at 1, or the slope of the tangent line to j at x equals 1 is equal to negative 4 times, that's be negative 6 plus 18, which is 12. So j prime at 1 will equal negative 48. Okay, that's sparse data, just enough data to get us where we want to be. All right, let's continue on the next slide. All right, number 3, I'm seeing a quotient rule. K prime at x is going to be g of x times the derivative of the numerator. The derivative of the numerator is going to require the product rule. So the derivative of the first function times the second, plus the first function times the derivative of the second. Okay, so let's make sure we know what we're doing here. Denominator, derivative of the numerator. Okay, now we have to subtract the numerator times the derivative of the denominator. Ooh, lots of stuff going on here. Over denominator squared. Oh, goodness. Okay, so k prime, and of course we had to throw a -2 in there just to make it nasty. That'll be g of -2 times the quantity f of -2 minus 2 f prime at -2. Okay, and then subtract. Now we're going to plug in a -2, so I'm going to make that plus, or minus -2 times f at -2, g prime at -2, oof, all over g of -2 quantity squared. Okay, so I'm going to try to keep this straight. You could pause the video and see if you can do the algebra right, or see if I do it wrong. So that'll be g of -2, which is -5, times the quantity f of -2, which is 3, minus 2 f prime at -2. So f prime at -2 is 1, times -2 is -2. Okay, well that actually makes things pretty simple. And then we'd have 2 times f of -2. F of -2 is 3, so that's 6, times g prime at -2. So 6 times 8, which would be 48, all over g at -2, which is -5 squared, so that would be 25. Let's clean this up just a little bit to finish. So k prime at -2 will equal -5 times 1, which is -5, plus 48, which is 43, over 25. Oof, that was a lot of algebra there. Okay, it's not the calculus that gets people, it's typically the algebra. All right, I guess I need that table. All right, let's look at L of x in number 4. Wow, this is a, a triple product rule. Okay, so imagine, we'll just lay it out here. So L prime of x. I'm going to consider, instead of doing a triple product rule, I'm going to do x cubed as the first function, and then f of x, g of x is the second function. So I'm going to have to do a product rule, but then I'm going to have to do a product rule within the derivative of the blue function f times g. All right, so let's see if you get what I'm saying. So the derivative of the first function would be 3x squared. The second function I would leave alone, f of x, g of x, plus the first function left alone, and the derivative of the second function. So the derivative of f times g is going to use the product rule again. So it'll be f prime times g plus f times g prime. Okay, that's a big mess. Now this question is asking a slightly different question. It's asking what g prime at 2 will equal if L prime at 2 is -48. Okay, so let's write everything out. L prime at 2, is it +2? Yes, it is equal to 3 times x squared. So that's 3 times 4, which will be 12, f of 2, g of 2, plus 2 cubed, which will be 8, f prime at 2, g at 2, plus f at 2 times, this is what we're looking for, g prime at 2. That's what we're seeking. Okay, so we need some values. Well, we know that L prime at 2 is -48. F of 2 looks like it is -5. So that'll be 12 times -5 times g of 2, which is 8. So 12 times -5 times 8. Well, it's going to be a negative number. Way to go. And what I'm going to get is 40 times 12, which would be 480. 480. So I'm going to get -480. Okay, plus, this will be 8 times the quantity. F prime at 2 is 3. And g at 2 we already knew is 8. So 3 times 8 is 24, plus f at 2, which we know is negative 5, times g prime at 2, which is what we are seeking. Okay, I can rid myself of that table. I don't need it anymore. Now I just have some algebra to do. Okay, let's see. What would be the best way to go about this likely? Okay, I'm going to add 480 to both sides. So negative 48 plus 480 would be 432. That'll equal 8 times the quantity, 24, minus 5, g prime at 2. All right, I think my best bet might be just to divide by 8. I think 8 goes into 432, and it does 54 times. I used my calculator, maybe you didn't hear it. That'll equal 24 minus 5, g prime at 2. Now I can subtract 24, well, this is going to be nice, which will give me 30 equals negative 5, g prime at 2. Oh yeah, look at that. So negative 6 is equal to g prime at 2 using some sparse data. Okay, let's keep it going. A couple of examples here. Number 5, this is an AP style question, so get used to this type of question. The table above gives values of the differentiable functions f and g and their derivatives at x equals 1. If h of x equals that thing, then what is h prime at 1? Let's find h prime at x, and then we'll sub in a 1. Okay, so I got product rule going on here. So the derivative of the first function is going to be 2f prime at x, right? The 3 would drop off, times the second function left alone, plus the first function left alone, times the derivative of the second, which would just be g prime at x. So h prime at 1 will equal 2 times f prime at 1. That'll be 2 times negative 2 times 1 plus g at 1. So g at 1 is negative 3. So this will be 1 minus 3 plus 2 times f of x, or 2 times f at 1. F at 1 is 3, so it'll be 6 plus 3, which will be 9, times g prime, times g prime at 1, which will be 4. So I will get h prime at 1 equivalent to, that'll be negative 4 times a negative 2, which will be 8, plus 36. It looks like h prime at 1. We'll see if our answer is present. It's 44, and I feel pretty darn good about that. Okay, let's continue. Another AP problem, consider this function. In order for f of x to equal 0, or f of x to be continuous at x equals 0, this shouldn't be here. That confused me. Let's get rid of the equals 0. In order for f of x to be continuous at x equals 0, the value of k must equal, well, we need for, first of all, f of 0 to exist. And I shouldn't write equals exists. I want it to exist. And in order for it to be continuous, specifically, f of 0 has to equal the limit as x approaches 0 of sine x over x. Well, do you remember that? Does that limit exist? I think you should. That's a special limit. So the limit as x approaches 0 of sine x over x equals 1. Therefore, for f of x to be continuous at x equals 0, k, which equals f of 0, must equal 1. Okay, now I should really scratch this. This is the continuity checklist. This is not part of it, right? I'm not writing a statement for the continuity checklist, but I'm basically filling in what f of 0 must equal, right? So in this case, I would be done at this point. You need to show some mathematical reasoning on any question, regardless of if it's multiple choice or free response, but I know then the answer here would be B. Okay, I think we got one more slide and we'll get it going. Okay, example 7. The equation of the tangent line to the curve y equals kx plus 8 over k plus x at x equals 2 is y equals x plus 4. What is the value of k? All right, so this is really interesting. If this is the tangent line, then the slope of the tangent line, at x equals -2 is 1. How do I know that? Well, because the slope of the tangent line is 1. Okay, so that means that y prime at -2 has to equal 1. All right, so I'm going to find y prime using the quotient rule. So that's going to be the low times the derivative of the high. Well, the derivative of kx plus 8 is just k, minus high derivative of low. Well, the derivative of the low is 1, right? Because the line has a slope of 1, all over k plus x squared. Okay, so we got to clean this up quite a bit here. So let's get to it. That'll be k squared plus kx minus, in parentheses, kx plus 8 over k squared plus 2kx plus x squared. All right, we have quite a bit of work to do here. So let's, again, clean this up just a little bit more. The denominator I'm actually okay with leaving it like that. But the numerator I want to clean up slightly. So the kx's will reduce, and I get k squared minus 8. Okay, so I want that to equal 1. All right, so if that equals 1, when x equals -2, so if y prime at -2 is equal to k squared minus 8 over k squared plus 2k times -2, that's our x value, plus -2 squared, and I want that to equal 1, then 1 equals k squared minus 8 over, let's clean this up, this will be k squared minus 4k plus 4. So if that equals 1, then guess what has to be true? The numerator has to equal the denominator. It's k squared minus 4k plus 4. Looks like we're going to end up, actually we won't have to factor, this will be great. Okay, so if the k squareds will reduce, right, if I subtracted 1, and then if I add 8, I get 0 equals -4k plus 4. Not 4, plus 12. Not sure why I didn't just subtract the 4 over, but that's all good. So 4k equals 12, so k must equal 3. So the value of k has to equal a positive 3 in order for the slope of the tangent line at x equals -2 to be 1. Okay, now notice that I didn't care at all really about that 4. I don't care. That's not part of the context of the question, so it's just kind of there as a distractor. All right, let's look at the last question for today. Example 8. This is an FRQ from 2006. This is the type of question that you'll see for an FRQ, at least for part A of a question. The twice differentiable function f is defined for all real numbers and satisfies the following. F of 0 equals 2, f prime at 0 equals -4, and f double prime at 0 equals 3. The function g is given by g of x equals e to the ax plus f of x for all real numbers where a is a constant. Find g prime at 0 and g double prime at 0 in terms of a. Show the work that leads to your answer. So let me copy g of x down here. That's e to the ax plus f of x. So g prime of x will equal a e to the ax plus f prime of x. All right, now I'm going to work with that in just a moment to find g prime at 0, but I'm going to write g double prime of x over here. I'm going to repeat the process, so I will get a times a e to the ax plus f double prime at x. I'm going to simplify that as a squared e to the ax plus f double prime at x. Okay, so now let's find g prime at 0. That'll be a e to the a times 0 plus f prime at 0. So g prime at 0. A times 0 is 0, so e to the 0 is 1. So I get a plus whatever f prime at 0 is. Looks like f prime at 0 is negative 4. So I could write this g prime at 0 is equal to a minus 4. Let's find g double prime at 0 as well. That'll be a squared e to the a times 0 plus f double prime at 0. All right, again, e to the 0 will be 1. So I'll get a squared, and f double prime at 0 is 3. There you have it, g double prime at 0, g prime at 0. That's it for today's lesson. That is 3.4, I believe, day number 2. See you next video.